Good morning, everyone. Am I audible? Can someone please confirm in the question chat box? Yes, I got the answer. So, hello everyone. Good morning. My name is Vatan Sharma. I welcome you all on the behalf of Midas IT for the webinar series that is finite element modeling and analysis of hydropower structure, presented by Chetan Agrawal sir. So, this is the sixth session of the webinar series, which is on pseudostatic stability analysis of NOF block and the model setup for the dynamic time history analysis. So before going towards the today's content, I would like to request Chetan sir to provide a brief recap of the previous session for the audience. So I'm making you presenter, sir. So presenter, yes. Now I'm unmute requesting. Just a minute, sir. Your voice is not audible.
Can you hear me now?
Yes, sir.
Unmuted.
Yes, sir. Yes. Yes, sir. Yes, sir.
Okay,
You
okay,
are
okay.
audible.
Thank you. Thank you. Welcome you all to this session of webinar. So you can see my screen also, isn't it, Vadan?
Yes, sir. Yes, sir. Yes, sir.
Okay,
I can.
okay. Okay, so in the last, I'll give you a brief recap what we did in the last session. In the last session, we extracted the NA block, deepest NA block, what we had to analyze, and we corrected this geometry. We provided one more inspection gallery at the top. Actually, the criteria is at about, I think, 25 or 30 meters. We have to provide one inspection gallery. That criteria is there, and we had shifted our this drainage gallery towards the upstream side so that we have a reduced uplift for normal operating condition, and for that also there is a criteria in various codes. I mean, as per that, we have amended this NOA block geometry. And uh, okay, so I'll quickly go through it. So it as you have seen that it doesn't take much time to correct the geometry. Okay, just this whole entire session was of about 1 hour, and within 1 hour I had corrected the geometry, I meshed it, I had applied all the loads. Okay, then the various loads I had applied, hydrostatic pressure due to the full reservoir level, then the normal tailwater, the pressure corresponding to normal tailwater level, maximum tailwater level also. Then for uplift, what I did, I created water elements here, a finite element water elements here. I had analyzed it separately to get the reactions at the base, as we have a inclined base here. Okay, so getting uplift, accurate uplift, that is a challenge. If we define function, I mean, it will be difficult to assess the accurate uplift at the gallery location at this inclined phase. So what I did, I mean, modeled these water elements and applied the load at the bottom, and then got the reactions there from the software, and then applied those reactions as a force at this inclined phase. Okay, so somebody asked me one question that it should be applied at the normal to the to this inclined phase. That is correct. It should be applied, the uplift should be applied normal to this phase. We should have two components of uplift here at this. One is upwards and another one is lateral, but we are checking this NA block for stability. For stability analysis from upstream to downstream forces, we are only concerned about the upstream to downstream forces and the vertical upward forces. But if you have to apply the I mean the normal force, the lateral force also, lateral component of uplift also, you can apply the the lateral variation of the hydrostatic pressure on these water elements itself, from the I mean from this inclined top to the to this base. Please remember that water exerts equal pressure in all directions at one point. So whatever is the hydrostatic pressure at this location, as per the elevation of this location, you can apply and vary it up to the bottom. So then you will get the reaction in lateral direction also. But for the stability analysis from upstream to downstream, we don't require it, so I haven't applied that. Okay, then so after that I got the reactions from the midas. Then I compiled those reactions, and this is a standard sheet. uh, I mean, from the standard sheet of Midas for importing the nodal loads, I imported those loads, those uplift loads here. Then I compiled all the loads which are applicable for construction stage, that is self-weight only, and for normal operating condition, that is for hydrostatic pressure corresponding to the full reservoir level and normal tailwater level, silt load. Those forces only I compiled. I just want to check whether my dam is safe for construction condition as well as the normal operating condition first. Then I'll jump to the other conditions, flood condition and seismic conditions. So this is what we did in the last webinar. We have compiled the forces, we have applied the forces, and today I'll be checking the pseudo-static stability for this dam. Okay, and for seismic analysis, I'll be setting up my model for dynamic time history analysis, and from next session, next 7th session and 8th session, that will be for dynamic analysis of the dam only. So I think this is it from my side at the moment. So over to you, Vatan. Thank you.
Thank you, sir. Thank you for briefing very nicely, sir. So I'm making my the presenter me. So show my screen. I'm changing the screen. So this is the monitor. So in today's session, like we start with the third.
So welcome you to this session of the webinar. In the last session, we had applied the various forces on our dam. So this will analyze our dam for the static analysis. Okay. So first thing we need, as I told you in the last session, we need the base properties. Okay. So probably what I'll do, okay, I'll paste this image. That would, then it would be easier to understand. Print screen, paint, cut it, Control X, paste it here. Okay. So this is our X axis, this is Y, this is, and vertical is Z. It is okay. Now we have to do a base area computations, base parameter. I want raft parameters. I want for that. I'll export this geometry. Export. Okay. Change first to this mode. Export. CAD file. One earlier some is there, so replace it. Okay. Go to AutoCAD. Then import it. Import this. Okay. Close. So when it will be imported, it will show a link here. Look at my cursor, link here, import job is in progress. So it will take some time, 1 or 2 minutes. So let's go to our sheet. So we'll see, we will have, so I have this length, width and area computations with me. So this, I have divided this rectangle in rectangular triangle and rectangular triangle portion, this raft, this bottom raft. So this is a rectangular portion. I can easily compute the area for this, and then the moment of inertia by parallel axis theorem BDQ by 12 plus AK square. Okay, and this inclined portion I have divided into this two triangles and one rectangle. So this is what I have compiled here. So this is the bottom rectangle, the bottommost rectangle, and this is this side triangle, and this one is rectangle of that inclined portion, and this is triangle. So I can easily compute the areas and the CGs and then moment of inertia. See, for inclined triangles and rectangle, for CGs, I'll be using this AutoCAD. Okay, so it is difficult to evaluate the CG. So now it is imported. So I just have to click. So it is there. So it is in block. Firstly, I have to explode this block to convert it to solid. Maybe I can check the volume of it so that I can compare it with the weight what I have evaluated from Midas. Say for that, mass prop command is there in AutoCAD. You must be aware of this. So say for this outer M20 concrete, the volume is 38,000 say. Okay, so let's see where is the, so this is this I was getting, so 38,000 volume I'm getting from the AutoCAD into 24. So it is about 9,100. So we have galleries and the lift well with 25 kilonewton per meter cube unit density. So it is almost same. So it can be this much. Okay. So then we need the properties of those triangle and rectangular in inclined portion. For that, again explore this entire block into surfaces. Delete this. I don't need this. Okay, I don't need this. Okay, maybe let's, okay, let's delete this and this one. Okay, and this one. Okay, let's see the coordinates here. ID, this coordinate, as you can see here, this is 0 0 213, the same as what we have considered. So x is this side, so let's see here, and y is this side. Okay, explode it again. I just need the lines. Okay, so CGs, I mean, I have to convert those triangle and this rectangle in inclined portion as region to get the mass properties and CGs from here. So for that, I'll use this 3D poly command in AutoCAD. Okay, I'll have this, and close. Okay, then I can create a region from this last closed region, closed 3D poly, this one. Okay, then 3D poly, this, oh no, this, this, and close. Okay, then again same region, last. Okay, 3D poly, this, and close. Then again region, last. So I have these regions with me. I can have mass properties. Okay, so need to get the distance. This distance, what is this distance? This is 2.14. I have already inputted it from the Midas. Okay, these parameters. Okay, then mass prop also I had computed it separately, so that no time is wasted. So see, for CGs, say I get the CGs here, 59.62 minus 10, 216.56. So for this, 59.62 minus 10 and 216.56 I have already inputted. So similarly for this triangle and this rectangle and this triangle also I have already included this. So then probably I don't need these regions anymore. I mean, I can just copy it okay, and paste it here. So for the easy visualization of the raft, okay, print screen, paste it in Paint, take it to your to the Excel, Control X. So this one, okay. I need the base pressures at various corners, say here. Okay, I'll be analyzing, I mean, like we analyze manually. Okay, this one, A, this is B, this is C, this is D. So for normal load case and for construction condition, I have compiled the forces in the last session. So we will see whether our dam is safe or not. For the construction condition and normal operating condition, we will go through the loading condition also. Okay, so let's group them. Maybe I can note down the coordinates also. A B C D E F. Okay, X Y and Z coordinates. Okay, X coordinate for this is 0, Y is also 0, and this is 213. Okay, so I have this here, so it's 213. B is this one, X, okay, Y again 0, and Z same as A, C same as X, same as B for X, and this is minus into which one, 5. Okay, rectangle is 5 meters in length. Okay, and Z is same, D, okay, X, what is X? So I have to check here. I can ID X. X is 58.91 minus 22, 23.69. 58.91. Okay. What is E? 6.95 to 23. Okay. So this will be same. I mean this one. Okay. This will be same as this. And this will be same as this. F will be 0. X, Y will be minus 5. Okay. And 213. So we have these coordinates with us and the raft parameters. Okay. I mean the areas which we have computed. Okay. Then the CGs of this raft, this inclined as well as this one. Okay, so this, and then moment of inertia. Okay, say for about the CG, let's evaluate the rough moment of inertia. Say this is length is 61 and here it is 51, 51, 52. Let's keep it say 55. Okay, average length into width is 20. BD cube projected length by 12. So it is almost same. Okay, so I mean this is just approximation, so it is matching with this, so this is okay. So we have raft area, we had compiled the forces for the normal construction condition and normal operating condition. Let's see the results for that, whether it is okay or not. See, okay, before that I'll go through the various loading conditions. Okay, so you can find the similar loading conditions in international standards also. I will be using Indian code IS 6512-1984. So these load combinations, these correspond to the usual, unusual, and extreme conditions. First is construction condition. Load condition is construction condition, dam completed but no water in the reservoir. Second condition is normal operating condition, full reservoir level, normal tailwater level, normal uplift, that is reduced uplift at the gallery location. Okay, then if ice is there, then we have to apply ice and silt we have already applied. Then C condition is flood condition, reservoir at maximum flood elevation. Here we have MW and FRL at the same level. Then all gates open, tailwater at flood elevation, normal uplift, okay, and silt. Then D condition, construction plus earthquake. E condition, norm B, load condition B plus earthquake. F condition, load condition C, but this was with normal uplift, this was with extreme uplift, that is drains inoperative. There is no release of uplift at the drain gallery location. Similarly for G, G also extreme uplift, E condition with extreme uplift. H condition is not used for stability. H condition, if you go through engineering manual 6051, this is used just to check whether there is no catastrophic failure in dam. I mean, dam is not completely failed and the entire water floods the downstream portion of the dam. So it will be analyzed for the stresses. Okay, there is a DCR criteria for that, whatever. Okay, we'll go through the engineering manual while carrying out the dynamic analysis, then we'll discuss this condition. Okay, and for evaluating the factor of safety against sliding, we will be using this formula. F is equal to net vertical force into the coefficient of friction between concrete and the founding material, that we will evaluate mu, that we will evaluate considering tangent of phi, coefficient of friction, you know this. Okay, divided by the factor of safety for the internal angle of friction plus cohesion into area divided by the factor of safety for cohesion, and whole divided by the lateral sliding force. Okay, so various factor of safeties for internal angle of friction has been provided in engineering as it's IS 6512. Similar criteria is in engineering manual 2200. You can check that and you can modify your sheet if you're performing your analysis as per that code or any other code. Okay, this I'm using this code. So for A, B, and C, that is construction condition, normal operating condition, and flood condition, factor of safety for internal level of friction is 1.5 and 3.6. For earthquake, these factors are factor of safeties are liberal 1.2 instead of 1.5, and this is 2.4. F and G, it is more liberal 1 and 1.2. F and G, extreme uplifts. Okay, and H condition we will not be using for stability. Okay, so let's see. So we have compiled the results. Let's see. Okay, so okay, so this vertical force I don't know. I mean, I have not compiled this correctly. So FRL I have compiled, normal tailwater level normal tailwater I have compiled, normal uplift drains operative I have compiled, and silt load I have compiled properly. So all other, I mean, values I'll compile it once my dam is stable in construction condition and this normal operating condition. So for construction condition, uh, there is no sliding, so we don't have any sliding force here. I have see for we should have these parameters with us, cohesion as well as the internal angle of friction between the concrete and the founding material with us. It is from the site specific studies. I have assumed something okay for this analysis. Okay, so it should be from the site specific data. Then we have to evaluate the pressures at various corner. So I can change these coordinates as per my raft. So okay, so but the shape of the raft is like this only. So at CG's location, this is X direction, this is Y, this is Z. For applying the loads, positive count, I mean clockwise, I have considered positive clockwise movements, all positive clockwise movements, and for summarizing it, I have considered the reactions opposite to it. So for applying the load, say upstream to downstream forces, I have considered negative because my X direction is in the negative direction. Okay, as you can see here. So for the reactions will be in negative X directions. So I mean the force application will be negative X direction, and for summarizing it, I have considered upstream to downstream as positive instead of negative, and similarly anti-clockwise as positive instead of clockwise. Okay, but for compiling it here, say for self weight, it's in negative Z direction, it will be applied. This is the direction of application of load, so this is will be negative. Okay, so let's see, say CG of this load, it will lie somewhere here. Okay, for this, for the construction condition, it will lie, I mean I just put it off and put my mesh on. Okay, so it will lie somewhere here. So this side. Okay, so you can check it from Excel sheet. This also, the CG is 36.77, the length is 61, so 61 is the total length, 30 is about 37 meters. It will lie somewhere here, and minus 9.5, minus 9.5, this is minus 20, so somewhere here, and 242.67, so it will be somewhere at the upper location, 242 point whatever we have evaluated. Okay, so then let's see for load combination A, the base pressures. So CG will be here. So based on that, B will have more pressure, E will have least. So let's see, B have more pressure and E have least. See, I have considered this torsional effect also. So torsion, say for self weight, there won't be any torsion, but for okay, so these I mean these are the pressures at various corners. Okay, that I have considered. Okay, probably I can link it to these coordinates, that would be better. Okay, 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 so this is now okay. So in all other load cases, it is linked with these cells, so this should be fine. Okay, so I have these load cases with me. Say we have maximum base pressure of this much, and if I convert it to MPa, this much MPa, and say if I consider factor of safety of 4, so we should have confined compressive strength of this much MPa for the rock to bear these pressures, 5 MPa. So these factor of safety and unconfined compressive strength, you should get it from site results, and I mean your geotechnical engineer will suggest what is the safe bearing capacity of that rock. It's a high dam. High dam should be founded on a sound rock. Okay, so it should be provided. So it's just I mean a check from my side. Okay, so I was talking about the torsional. So I'll discuss it here. In B condition, we have water pressure corresponding to FRL that will induce some lateral force and vertical component also. Okay, and then the movements, I'll discuss these movements. Okay, then silt load we will have normal tailwater level, and uh, that will be having a passive resistance from the tailwater side, and we have vertical weight also, and the uplift will reduce the weight, you know this. So this is safe again for the sliding. Let's check it for the what you call base pressures. These coordinates are not correct, so it is, so I have to correct it as per my raft. Okay, so see, this is actually 61. Okay, this is 61, this is fine, and this is 58.91. Okay, This other things are, I think, fine. Okay. See, this is in X direction. Okay, I mean these. So I mean we will have a FRL water pressure from this side that will increase the base pressures here. Okay, but weight will counter that. Okay, so we will have what you call reduced pressure at B, C, and D than A, but the more pressures at A, F, and E. Okay, we'll have silt. Some pressure will be induced here due to the silt load, but vertical component will also be there that will increase this side. And similarly, we have passive resistance from the normal tailwater level also, but uplift will reduce the weight. So it's the combination of everything. And then MZ. See, for this hydrostatic pressure FRL, it's not a uniform distribution. So the CG will lie somewhere here, and that will induce some torsion, and that will increase the pressure on towards F and E more. Okay, that pressure into EY, that will be the MZ, but in that is in anti-clockwise direction, so that will include this. So I mean this, for this torsion, I'll be considering the moment of inertia about this x-axis, and for upstream to downstream forces, and from across flow, there is no force in this particular case, but we can have some static earth pressure or surcharge pressure. For that, say this into some eccentricity in x direction, that will induce that torsion. So this I have considered. I mean, if I remove this MZ, so there will be only slight change. Okay, say maximum is, say, what, 1168 is the pressure, no? So now it has in fact reduced to 1114. Okay, so this torsion effect will have a lesser impact, but it will be there, so I have included it. So in B case also everything is fine, but this pressure is slightly less anyways, but these are all positive. This is what we want. So for other load cases I have to compile the results first, so that I'll do now. Okay, so MWL, it is same as FRL, so I'll have this TX and TZ, copy it, okay, and paste it here. Then we have normal tailwater level already compiled. Maximum tailwater level I will compile now. So I have these analysis cases with me. Go to post processing mode, and then maximum tailwater level, this one. Okay, so we have grid forces in X as well as in Z direction. So none. I'll need this one. Okay, copy it and paste it here first. Okay, then copy it and paste it here. TY I'll not have for tailwater level, but Z, TZ definitely I'll have. Okay, I mean the vertical component of normal tailwater level will induce TZ force. Copy, paste it here first, then copy and paste it here. Okay, then normal uplift drain operative I have. See, drain in operative conditions are for F and G, that I'll do it separately. I have to, I mean, perform the similar analysis I did. I mean, this uplift case, this uplift case, I have to, I mean, compile the results, then take it to the Excel sheet, then I import it again to this. So I'll do it later on. So let's not waste our time on this. So these are only for the two load cases, F and G load combination cases, that I'll do later on. Uplift, okay. Maximum uplift also, that is not required here. So I'll have silt load. Okay, so silt load I'll compile. Silt load, again we will have two components. Silt load I have already compiled, okay, for B condition. Then hydrodynamic I'll compile. We will have only one component, hydrodynamic in x direction, grid force, show table. Okay, none. Okay, copy, paste it. First paste it here. Okay, then copy it and paste it here. Then we don't have static earth pressure, we don't have surcharge pressure, seismic inertia we have in two directions. Copy, copy and paste it here. Okay. Then the last one, TZ, TY won't be there, and TZ. Copy, copy and paste it here. Okay, so we have compiled the results except for F and G case. For all other load cases, I have the results with me. Okay, so A condition we have checked, B condition we have seen, although this pressure, I mean, B, C and D, these pressures are less, but these are, I mean, as per the codal requirements, these are all positive, so it's fine. For A and B condition, our footing is not in tension. Let's see for C condition, that is flood condition. Flood condition actually here, full reservoir level and maximum flood level, those are same for this particular project. So it will be similar to what we got from uh, the in B condition, in normal condition. Okay, only difference is the maximum tailwater level will induce lateral as well as the vertical force also on the downstream side. So I mean it will be almost similar to that 11670 what I was getting here 1168. So it is similar. Okay, then the D condition, D is the seismic condition. Okay, so I have evaluated the stability for seismic condition in this sheet. So for seismic condition, I have considered earthquake upstream to downstream, downstream to upstream and upwards. Okay, then then downstream to upstream, downwards, downstream to upwards. I mean all the combination upstream to downstream upwards, upstream to downstream downwards, downstream to upstream upwards, and downstream to upstream downwards. So these four combinations I have considered. So there will be some lateral force due to this seismic inertia force. Okay, other than that, only self weight will be there. So it is similar to A, but with earthquake. Okay, so we have a lot of safety margin here. In base pressure, similar to earthquake, similar to A condition. A condition, B, we will have more pressure at B because the CG of weight lies here. But because of seismic inertia force from upstream to downstream, it will increase the pressure at A, at F and D, and it's upwards also. So it will reduce the what you call the net vertical weight. You know this, okay? So let's say A, it will be, I mean, more than load as compared to load combination A. So it was in load condition A, it was 390, and for load combination D, it is 537. Okay, so yes, so it's you must be having your own sheets. Just follow that. Okay, so everything is okay here, no issues. So now let's see the so okay, this one is actually for the time ground motion time history. I have checked factor of I will check that factor of safety against sliding for each cycle, each time cycle of ground motion time history. This is not for this project. I'll perform this analysis and then I'll be doing it. I'll let you know, I mean, later how it is performed when we will perform the dynamic time history analysis. Okay, let's see E condition. E condition is the B condition, normal operating condition plus earthquake. Similar, I mean, earthquake forces I have condition as I had considered for D condition. Okay, so for this factor of safeties are okay. So I have so F and G condition I have not considered. I have summarized these results. Let's see here. So as you can see, A, B, and C all are positive. D also everything is positive. E we have some negative base pressures on this side, B, C, and D. B, C, and D. Other than that, on this side, A, F, and E, A, F, and E. These are all positive. So we can have negative base pressures here. Okay. So I mean, engineering manual says that resultant should lie within the base. That is the only criteria, that entire base should not be in tension. So this we have ensured. F and G we haven't done. Next, for extreme uplift, I have to compile the results here for F and G. So let's go to the Midas window. So I'll set up my model for the dynamic analysis in this session. I'll apply the seismic wave. Okay, I'll model the foundation. Okay, so actually I'll be using this mesh set only. So I have applied all the loads. So I'll have all the loads with me for dynamic analysis. For dynamic analysis, I'll be considering provisions of USAC Engineering Manual 6051 and 6053. So we'll be discussing the applicable clause for gravity dam in the next session when it is being analyzed. So analysis will take some time. Dynamic analysis takes some time. While the software is analyzing, we'll discuss the code. Anyways, for the dynamic analysis, first we have to model the foundation, and I'll be using this mesh only. I'll extrude this mesh for the foundation. Go to 3D element face. Okay, no, that's fine. Okay, and direction is vertical. So see, I'll be modeling about 100 meters in vertical direction and on each side of the dam. So it's in one of the example in USAC Engineering Manual, they have also modeled the depth equivalent to the height of the dam, and on either side also almost equal to that. And it's mentioned there somewhere, I mean, in the engineering manual itself, we should have enough foundation quantum model here, so that the prominent deformation bulbs are within the modeled uh, quantum. Okay, we'll discuss that later on, but at the moment I'll be modeling 100 meters on each side. So let's say first I'll model this, say about 20 meters. I'll model minus 20 in vertical direction. Reason we can have a coarser mesh here, say for this, I mean for the first layer of rock, I'll say keep 5 meters. Then I have to define the rock properties. So rock layer 1, I'll name it rock layer 1. Okay, so and properties, instead of isotropic, I'll choose orthotropic properties. So we have various orthotropic models here: jointed rock mass, 2D geogrid, whatever. So I'll be using, say, linearly transversely isotropic. So 1 2 3 4 5 6. So this seems to be less for rock, so I'll put one more 0 here. So in other direction, transverse direction also, I'll keep it as it is. So 0.15, I'll keep Poisson's ratio. In this direction also, I'll keep 0.15. Put one more 0 here. In the 2-3 plane also, I'll use this. Let's keep the other thing same, layer 1. Okay, apply. I'll have say 3-4 layers here, layer 2. Maybe I can another thing. Yeah, okay, one more thing. Density I have not defined. I have to define the density also for this. See, I can have massless, dampless foundation. I can use these I mean porous parameters, various poisons, I mean void ratio, unit saturated, unit rate, whatever, permeability coefficients. Okay, I can have water table, so I can have various geotechnical properties inserted in it. So for various layers of so those are more applicable for soil. We have to carry out liquefaction studies. Okay, so for sound rock in confined environment, that will, I mean, during earthquake, that will vibrate almost in phase. Okay, so we are more interested in the structure constructed above it. That foundation, it has undergone various earthquakes, various other forces, and it is stabilized now. If it is say RBM or loose material, then we are, then these are of more interest. Anyways, so actually in USAC Engineering Manual 6051 also it is mentioned that we can model the dampless dampless massless foundation to get the maximum response at the structure. So this is the simplistic approach. So I'll be using that only. I'll put 0 here and without any damping. Okay. In the code, it is mentioned that we should start our analysis with the simplistic analysis, pseudostatic simplistic seismic coefficient method analysis that I have already done. So for this also, okay, before moving forward to the more refined, complicated analysis, sophisticated analysis. So I'll be using dampless and massless foundation here, layer 1. Okay, so I can copy this, save one more time. Okay, modify, say this is layer 2. Okay, I can have other models, so let me keep it this one only for the timing, and this also 4. This I'll increase to say 10 instead of 8, 10. Okay, it should be as per the site. These parameters should be as per the test results of the samples collected at the side of the foundation from borehole data, whatever we had corrected. So I'm considering some arbitrary values here. Okay, so layer 2 is fine. Then say layer 3. So I'll consider layer only 3 layers here. So layer 3. Okay, say 5. So then say it's 12, whatever. So these are all assumed parameters. Okay, and okay. So rock layer 1. Okay, and this, let me check. So it is okay. Okay, now this. So probably, I mean, I can align these nodes at this plane. So I'll change my work plane. Okay. Hash. Just select these nodes. Okay, and where to this? Okay, and direction in vertical direction. Okay, so it's fine. I don't need this. Okay, and then I can see, I'll require the interface element in between these two. So so we can compute the interface properties manually. That is the normal stiffness modulus as well as the shear stiffness modulus using various equation, whatever equation we want to use. We can use Coulomb's theory or Coulomb's friction theory or Timoshenko's formula, or there are a number of formulas for that. Whatever geotechnical engineer suggest, those parameter we can input. And Midas also has this inbuilt tool for creating interface element. So I'll be using that tool only. It is based on the Coulomb's friction theory. So for that, we have to consider the mesh set, and so the interface will be created in between these two materials, whatever is in contact with this mesh set. And then I'll consider this inbuilt wizard here. So this thickness factor, it will define the compressibility of this. Lesser the thickness factor, that means we have a strong interface element, strong material. So I'll keep say 0.02, whatever. I don't want to reduce the strength of this interface element. Let's keep it. I don't want rigid link in between these two materials. So let's put it off and we'll create an interface element. So it is created. Let's see. Okay. So put it off. Say I'll rename it to say rock layer 1. Okay. Now I can what? Okay. Okay. No worries. So I can now extrude these mesh faces. These mesh faces in X direction, in lateral direction. Okay. Select direction. This one. Okay. And say in this direction also it's 100. And say coarser mesh of say 10 meters, 10 meter. Okay, don't worry about this. We'll change the parameters and mesh set later on and apply. Okay, similarly this side. Select direction, this one, positive 100 meters and apply. Okay, then in this direction, vertical direction. Okay, and this one direction is vertical. Okay, I've already modeled 20 meters, say 70, 80, 90, 80 meters I'll have, minus 80 and 8 divisions. And okay. Okay, so this is the rock layers. So this is rock layer 1. I'll include all the elements up to here in rock layer 1. Apply. So probably I'll rename this to rock layer 2. Okay. And include these elements here. Okay. And this I'll rename to rock layer 3. And this I'll rename to rock layer 4. Okay. There's rock layer 3 is up to here. Apply. Okay. And the rest is rock layer 4. This one. Okay. So I have these various rock layers. I have to change the properties also. Go to parameters. Okay, 3D rock layer 1 I have. So this one is rock layer 1. Apply. Then I need to define layer 2 properties. Layer 2. Okay, and this layer 2. Okay. So select these, and apply. 4 layers are there? No, 3 layers are there, no, only. Okay, anyways, layer 4, layer 3, layer 3. So let's keep this all the bottom mesh as layer 3. Otherwise, I can create one more layer for this. Okay, anyways, so probably I can combine these. Okay, so this is the setup of the foundation. Now this I can actually align this in the XZ plane. So for that, I mean these oblique nodes. Okay, 3 points. Okay, then project these nodes to this node in this direction. Apply, or just cancel it. Okay, then translate this surface to on this side also. Okay, and same exercise I'll do it for this side. Project these nodes okay, so now I can remove this. Okay, see this is unnecessary creating issues, so water I'll remove. Okay, I don't need this. See, now I have to define the seismic waves. So we should have site specific seismic data with us. So we have design basis earthquake and maximum credible earthquake, site specific time ground motion time histories for that too in horizontal as well as vertical direction. So I have this data with me. So for that we have to create one time forcing function. So this is the time forcing function. Add time forcing function, say dbe horizontal. Okay, horizontal db, copy and paste it here. So you can see this seismic wave ground motion time history, and it is normalized to 1. So that means while analyzing we have to I mean that means the peak ground acceleration, whatever is that is actually considered as 1, and based on that other accelerations are I mean computed considering this as 1. So for while analyzing we have to multiply it by peak ground acceleration for the dB condition for this. So 0.12 is our seismic coefficient, so we have to multiply it with that. Okay, apply. So dB vertical, copy it, copy and paste it here. Apply. MCE maximum critical earthquake horizontal, MD or MC whatever. Okay, with MC horizontal, copy, apply. So you can see the maximum peaks are, I mean, in between 2 cycles, time, I mean, 2 seconds to say 8 seconds. Okay. So our structural response will be maximum up to, I mean, within 8 seconds, then it will start reducing. Okay. Anyways, so we have this, okay, apply, and then MC vertical. Yes. Copy and paste it here. Okay. So we have defined our seismic wave functions. See, I'll be applying this ground motion time history from upstream to downstream. Okay. I'm analyzing this dam block from upstream to downstream forces. So actually, seismic wave, it dissipates at some distance from the epicenter. I mean, it doesn't continue up to the entire Earth. Entire Earth doesn't shake. If some earthquake is there in, say, India, America would shake. So it will dissipate. So we can't model entire Earth. So see, if we provide the normal constraints, side constraints here, okay, we have to provide some constraints to analyze the structure. If we provide that those normal constraints here, it may happen that seismic wave which is traveling here will reflect back, and by that time the structure may not have regained its original position, so that seismic wave will again strike it. And I mean, the structural behavior may not be correct if we apply the conventional uh, constraints, side constraints here. Okay, for that there are absorbing boundaries. It is mentioned in engineering manual 6512 that we should have provide the absorbing boundaries here so that the seismic waves are absorbed. So superior to absorbing boundaries, we have free field boundary elements which absorbs whatever wave we have I mean applied. So I'll be using this free field element. Go to create free field and plane. Okay, so for this face and this face, I'll have free field elements. Okay, I have to define the property here. Okay, say free field. Okay, we have absorbing boundaries, absorbent boundaries also, but free field is better, so we'll keep free field. Okay, and I'll create these elements. So these free field elements are created. Now boundary constraints for static analysis, I had provided these boundary constraints. I'll remove this and I'll provide these boundary constraint at the bottom. The bottom I'll keep as completely restrained as mentioned in engineering manual. Okay, so this is my setting for the mm, dynamic analysis. I'll carry out dynamic analysis in the next session. Okay, so probably I can, okay, create a case here. See, we can provide densities of these rock layers. Okay, and we can then simulate the construction stage analysis. Okay, for performing a this dynamic analysis. In first stage, uh, we we can uh, we can consider that no deformation is there because of the self weight of the this rock medium. So it is already stabilized. So this we can consider in construction stage analysis. But in construction stage, we cannot simulate linear time history. We don't have option of linear time history in construction stage. Construction stage, otherwise also it is a non-linear analysis. So I'll not be using construction stage. Otherwise also I have considered the zero mass here. So it will not deform due to the self weight. I mean this foundation. This foundation is only providing the stiffness properties. So it won't deform due to the self weight of the what you call foundation. So I'll create a analysis case for dB time history. Change the change it to say linear time history. Direct I'll be using, so we will be, discussing direct and modal time history in the next session while going through the code. What does it mean? So I'll mention DB time history. Time steps I have to define. Say I'll name this time step as T1. Say as we have seen that up to 8-second maximum response was there and time step was 0.01 for this time history. Okay, 0.01. Okay, so I'll keep this add. So it will up to it, and specific output I'll require at each time step, so I don't have to specify anything here. Okay, then analysis control. See, geotechnical setting, I don't have to do any geotechnical setting. I don't have any self weight. I don't want any earth pressure to be applied here, no porosity, whatever. So I don't need these. Dynamic. See, dynamic method, we have this railing damping coefficients we have to provide, but that is also not applicable for massless dampless foundation and with this free feed boundaries. It will give some erroneous results. These are more applicable for the loose, somewhat fractured rock and those. Uh, so please go through the railing damping parameters. You will find a curve, and see, if we have to provide it, we have to be very careful for while providing this. Midas can also compute these parameters based on the frequencies of two modes. These two modes, actually, these are not first mode and second mode. This can be, but see, you have to consider those modes where we have the linear distribution of where we can have the linear distribution of these mass proportional and stiffness proportional. You please go through that relic uh, these mass and stiffness coefficient curves, so where it is somewhat flatter and linear, so those modes we should provide it. But in this case, for dampless massless hard rock, we should not consider this when we are also applying the free feed boundaries. So it may give erroneous result. We can have 0 values, or we can have some value here, so, and another value here. Okay, because some equal values we should put for mode 1 and mode 2, so that we don't have these values. Okay, so damping ratio, again, we don't need. Clear. Okay, and see this Newmark block again. See, Newmark block, what I understand is that it, see, at some acceleration of, say, ground or different layers of rock, the above layer will start deforming at some acceleration. Okay, so that Newmark block analysis is, that means, more applicable where we have layers like in Rockfill Dam or earthen dam. Okay, at some particular ground motion or at ground acceleration, that material will start moving. So we can consider constant acceleration here for concrete gravity dam. Concrete gravity dam, different layers of concrete, different levels of concrete. That in between we have, immense cohesion. So in concrete gravity dam, we are more concerned about the stresses, induced stresses. DCR criteria, demand capacity ratio criteria, and cumulative inelastic duration criteria is more applicable in concrete gravity dam. We will go through these criterias in the next session. Okay, so this is it. Let's keep everything same. Okay, then this water I have removed. No, so all these layers I will require boundary set 1 I will require, and I have not defined the dynamic load. Dynamic load I have to define, and it's quite simple. Time varying ground motion, ground acceleration. Okay, ground acceleration in x direction, dB horizontal minus 0.12. I have to multiply it with minus 0.12, and z direction dB vertical, that was 0.08. Okay, I'll name it dB. Okay, so I'll edit this. I have this dynamic load with me. Okay, so my setup is ready. So in the next session I'll analyze it, and then we'll check the stability against sliding for each cycle. Actually, it is not required for the dynamic in frequency domain. It is mentioned in USAC Engineering Manual 6051. We'll go through that. But I'll perform this. Let's see. I mean, whether the factor of safeties are within the permissible limit for each cycle of this time history, for even for the maximum ground acceleration, whether the sliding is okay or not. Okay. So this is it for this session. See you in the next session. Thank you very much.
Thank you, sir. Okay, so audience, if you have any questions, you can write it in chat box. Chetan sir is also there, so he will answer your questions. I'm making presenter, Chetan sir, you. Just a minute. Yeah. You are presenter, sir, and
So
you are.
can you
Yeah, I can hear
am I
you.
audible?
Yeah. Yes, sir.
Yes,
Yes, sir.
yes. Okay, fine.
So,
Can
sir,
Vatan, can you please go through the questions so that I can
yes,
answer?
sir.
Yes.
Sir, good. This is question from Bharat. If
Mm.
we are modeling and analyzing one dam block, what should be the constraint at the side face of the dam?
Side face of the dam, you should apply the free boundaries or free field boundaries or absorbing boundaries on the side face of the dam. At the bottom, you can keep it completely constrained as I have shown. Yeah, because otherwise seismic wave will reflect back and your the structural behavior will not be accurate.
Yes, sir.
Is it okay or?
Uh,
Yeah, yes.
yeah, yeah. So
Yeah.
the next question
Mm.
is that mode 1 or 2 you said we have to do eigenvalue analysis first, and from there we have to take the value for each for which the mass participation is more, right, sir?
Okay. Okay. Actually, see, we are very much, I think, obsessed with eigenvalues, these sort of things. See, time history analysis can be performed in two ways: modal time history and this direct time history method. Mode shapes, those define the boundaries in what you call vibrational environment for this modal time history analysis, or for that matter, response spectra analysis also. For dynamic time history, for each cycle, all the masses will participate. For direct time history is more refined, where the mode shapes, time periods are not of much concern. Okay, we will go through engineering manual 6051 and you will find it is specifically mentioned there. Okay, see, for relic damping parameters, relic damping are normally used where we have a disturbed damping of the material in our model. Say we have RBM is there, we have some loose fractured rock is there at the founding level, or say soil is there, or say earthen dam is there. So there is a variation of damping is in the material. For if the variation of damping is there, then these Rayleigh mass and stiffness proportional should be used. Otherwise, for hard isotropic material like concrete or a sound rock, okay, so these are these Rayleigh damping modal participation, if we are considering modal sorry direct time history method, these are not of much use. Entire dam, entire masses will participate in each cycle. Okay, and whatever constraints we have applied, actually applied on the model, that will be actually define the boundary constraints for direct time history method. So it is not dependent on mode shapes or whatever. I'll show you in the next session. We'll go through that code and I'll show you that. Okay, so eigenvalue analysis is not required for direct time history method.
Okay, so
Yeah.
thank you, sir. Next question is from Henry. What is the engineering manual the presenter keeps mentioning?
Yeah, first thing is for the loads, you can go through USAC Engineering Manual 2200. I mentioned it in captions also. For dynamic analysis, please go through USAC Engineering Manual 6051. You can Google it. You can download it for free.
Okay.
It is available on the open domain. Yeah.
Mhm. So the next question is, when the NOF block is abutting the rock, what will be the interface between the dam block and the rock?
That you have to find out as per the properties of the abutting rock and the concrete, of course. That you can use various methods. So better to consult a geotechnical engineer to get the interface properties for the, I mean, the shear stiffness modulus and normal stiffness modulus. Okay, in between the two phases, it depends on the properties of the rock.
Okay, okay.
Yeah.
And there is one question. CP and CS values needed can be calculated from the shear modulus,
Of
Poisson's
course.
ratio. Yes, of course.
Yes, yes, you can compute that.
Mhm.
Yes. Yeah.
Anyone different? You have any questions? Please ask in the chat box. I will read and Chetan sir will answer it. Okay. Any questions? We are here to answer your questions. Please ask. Henry said that I can't get the name clearly. Please type the name. Okay, I will, sir. I will personally mail you
Okay.
if you have used your, yeah, I will definitely mail them.
USAC Engineering Manual 2200 and 6051, and you can also go through 6053.
Nirmal said thanks for the sessions. If you have any questions, please ask, audience. I think, Chinitha, that's it for the questions.
Okay.
I think we answer all the questions. If we miss, like, because the question box is very small, if we miss one of them, we will answer them personally through the email. Okay, no issues in it. Okay. Okay, Chetan sir, thank you for
Okay.
oh, sorry, one question is again asked by Gouda. How much depth and the width of the rock do we need to model?
See, as I said in the, I mean, while in the webinar also, your prominent deformation bulb should lie within that quantum of foundation. It's, I mean, in engineering manual also in examples, they have modeled the depth equivalent to the height of the dam, and on the either side also, whatever the height they had modeled that. So that should be fine. But if your, it all again depends on the material. If your prominent deformation bulb exceeds that, then you may have to, I mean,
Hmm.
increase your model boundaries. But see, if you are using free feed boundary elements or absorbing boundary elements, I mean, that much of extent, the height of the
Hmm.
dam, that should work fine. Yeah, no, in
Hmm.
normal cases. But you have to go
Yes,
through
sir.
the deformation bulb, I mean, after the
Yes.
analysis. Yes.
Yes, sir. Yes, sir. If we go with the thumb rules that your lateral boundary should be double the height of the dam and the bottom boundary is the is equals to the height of the dam, that we can also use. These are general thumb rules, I think.
Yes, 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 of course.
Mhm.
Yeah.
The next question is how to define reinforcement in concrete dam.
Concrete gravity dams, actually we don't provide reinforcement. That this is what we are analyzing. I mean, on the upstream phase, DCR criteria is there. We have to, we don't allow any tension for normal operating condition and construction condition on the upstream phase. Okay. And see, we don't provide reinforcement on the upstream phase. Yes, for surrounding the galleries and in the flexural components like lift well, staircases, reinforcement is required. For that is designed for bending moment and shear forces. Concrete gravity dam reinforcement is not provided. Tension are limited for various operating condition. There are various limits provided in the code. We have to abide by that, so that no tension, no reinforcement is required in the uh, uh, I mean, concrete gravity dam. If at
Yes,
all,
sir.
if it is exceeds and we have a limited, we can't increase the section of the dam. Sometimes we have to in the foundation and on the upstream face also, but normally it is not provided.
Thank you, sir. Thank you for answering this question. Okay, I think that's all for the questions. We have not received any questions yet. Thank you, Chetan sir. Thank you for providing these useful and informative sessions to all the audiences. And I would like to request the audience, please join for the next sessions too, in which sir told you about the dynamic analysis of the dams and what the results you have to get from the dynamic analysis, like tension, principal stresses. We will discuss these in more detail in the next coming two sessions. So please join us for the next sessions. Thank you, Chetan sir. Thank you.
Thank you. Thank you.
Thank you, sir. Thank you.
Bye.
Bye bye, sir.